So very good evening to all people. So my name is Mohammed Majid Febri. My number message is EG220043. So today I want to make some of presentation or like about five topics that we include in this slide, which under for the event for the exam of subject BDD 10102 electromagnetism. So without further ado, let's go to our first chapter, which is Fleming handbook. So choosing to follow the law electromagnetic induction when a conductor moves through a magnetic field and electric current is induced in it. Fleming right hand rule is used to determine the direction of the induced current. So Fleming right hand rule says that if we arrange our thumb, forefinger and middle finger of the right hand perpendicular to each other, then the thumb and then the thumb points towards the direction of the motion of the conductor relative to the magnetic field. The forefinger points towards the direction of the magnetic field, and the middle finger points towards the direction of the induced finger current. So actually, we use the Fleming right hand rule, which says the thumb is to show for thrust or motion, for the for the for the forefinger, which show the magnetic field, and for the middle finger, the uh, indicator for the current. So it was also applied at the Fleming hand rule, which when the current carrying conductor is placed in an external magnetic field, the conductor experiences a force perpendicular to both field and the current flow direction. Fleming hand rule is used to find the direction of the force acting on the current carrying conductor placed in a magnetic field. Fleming's left-hand rule states that if we arrange our thumb, forefinger, and middle finger of the left hand perpendicular to each other, then the thumb points towards the direction of the force experienced by the conductor, the forefinger points towards the direction of the magnetic field, and the middle finger points towards the direction of the electric current. So eventually, just just as just the same as the Fleming right-hand rule, but actually the difference was to show the thumb shows the thrust of all the motion, the the forefinger the forefinger show us the magnetic field, and the middle finger show the current. But so what's the difference between Fleming left hand and right hand rule? So we can observe that the left hand rule is applicable to the motor and right hand rule to the generator. Fleming left hand rule and Fleming right hand rule are a pair of visual mnemonics. Mnemonics are learning technique for memory aids, such as abbreviation rhyme or mental image that help you to remember something. In practice, these rules are never used except as a convenient trick to determine the direction of the resonance, either current or thrust. What gives the magnetic force along this direction determined by this rule is the Lorentz force. So the difference is for the Fleming left-hand rule, first is used for the electric motor, while Fleming right-hand rule is used for the electric generator. And the second is the purpose, which the purpose for the left-hand rule to finding the direction of the magnetic force acting in electric motor. Meanwhile, for the right-hand rule, we use this rule to finding the direction of the induced current in an electric generator. And for the middle finger, represent the direction of current, and while the middle finger represent the direction of the induced current. So for the next chapter, we move to the Gauss law. So in the Gauss law states that the net electric flux through any particular closed surface is equal to 1 per E0 times that the net electric charge within that closed surface. With surface 1, the electric field is upward for all points on the surface. Thus, the flux of the electric field through the surface is positive, and so is the net charge within the surface as Gauss law requires. Surface 2 is this surface enclosed. No net charge because the enclosed positive and negative charge have equal magnitude. Gauss' law requires that the net flux of the electric field through the surface be zero. And for the surface 3, the surface enclosed no charge and the term enclosed same as zero. Gauss' law requires the net flux of the electricity field through the surface be zero. That's reasonable because all the field lines first integrate through the surface, entering on the right and leaving on the left. So in the electromagnetism, Gauss' law, also known as Gauss' flux theorem, relates the distribution of electric charge to the resulting electric field in its integral form. Gauss' law relates the charge enclosed by a closed surface, often called a Gaussian surface, to the total flux through that surface. When the electric field, because of its symmetry, is constant everywhere on the surface and perpendicular to it, the the electric field can be found. Gauss' law and Coulomb's law are different ways of describing the relation between charge and electric field in such a situation. In such situations, Gauss' law is easier to apply than a Coulomb law. Gauss' law involves the concept of electric flux, a measure of how much the electric field vector penetrates through a given surface. So, Gauss' law is also a useful method for determining electric field when the charge distribution is highly symmetric. It was developed by Mr. Carl Friedrich Gauss, a German mathematician and physicist like Ampere law, which is an analog to magnetism. Gauss' law is one of the four Maxwell equations, the first and thus fundamental to classical electrodynamics. Also, Coulomb's law involves the concept of electric flux, which refers to the electric field passing through a given area in words. Gauss' law states that the net electric flux through any particular closed surface is equal 1 to per the time that the net electric charge within that closed surface. Just like the memory they given. So, application of Gauss' law essentially is very useful for determining electric field when the charge distribution is highly symmetric. In choosing the surface, always take the advantage of the symmetry of the charge distribution so that E can be removed from integral. In order to apply Gauss' law, however, we must use the Gaussian surface recurrence so we can determine E. So we can normally try to think of a surface that has symmetry needed so that it will be constant on all or on part of the surface. So just like when we can see the image, we have the point charge and then when the line charge and sheet of charge, when we have the conducting sphere, then conducting cylinder, when it's a sphere with uniform charge density and cylinder with uniform charge density, and the change on the surface of that conductor. So we go to Biot-Savart law. We have seen that mass produces a gravitational field and also interact with that field. Charge produces an electric field and also interact with that field. Since moving charge that is current interact a magnetic field, we might expect that it also create that field and it does. Biot-Savart law is an equation that gives the magnetic field produced due to a current carrying segment. This segment is taken as a vector quantity known as the current element. So in the Biot-Savart law, considering a carrying wire I in a specific direction as shown in the above figure, take a small element of the wire of length. The direction of this element is along that of the current, so that forms a vector. To know the magnetic field produced at a point due to this small element, one can apply Biot-Savart law. Let the position vector of the point equation drawn from the current element Br and the angle between the two be theta. When the U when the UO is the permeability of free space and is equal to 4 pi 4 pi multiplied 7 psi negative 1. The direction of the magnetic field is always in a plane perpendicular to the line element in its position vector. It is given by the right-hand thumb rule, but the thumbs point to the direction of the conventional current and the other finger show the magnetic field direction, just as what the picture shows. So application of Biot-Savart law and importance of Biot-Savart law. So every law has an application importance. So for Biot-Savart law, the application is we can use Biot-Savart law to calculate magnetic response at the atomic or molecular level. And it also uses an aerodynamic theory to calculate the velocity induced by the process line. So the importance is the Biot-Savart law is similar to Coulomb's law in electrostatics, and the law is flexible for very small conductors to which carry current, and the law is applicable for symmetrical current distribution. So for the fourth topic, we go to Faraday law. So Faraday law of electromagnetic induction, also known as Faraday law, is the basic law of electromagnetism, which helps us predict how a magnetic field could interact with an electric current to produce an electromotive force or EMF. This phenomenon is known as electromagnetic induction. Michael Faraday proposed the law of the electromagnetic induction in the year 1831. Faraday's law, or the law of electromagnetic induction, is the observation or result of the experiment conducted by Faraday. He performed the three main experiments to discover the phenomena of electromagnetic induction. So Faraday's law of electromagnetic induction consists of two laws. The first law describes the induction of EMF in conductor, and the second law quantifies the EMF produced in the conductor. In the next few sessions, let us learn this law in detail. So the discovery and the understanding of the law of electromagnetic induction are based on a long series of experiments carried out by Faraday and Henry. From the experimental observation, Faraday concluded an EMF is induced when the magnetic flux across the coil changes with time. Therefore, Faraday's first law of electromagnetic induction states the following: whatever the conductor is placed in a very magnetic field, an electromotive force is induced. If the conductor circuit is closed, a current is induced, which is called induced current. Mentioned here are a few ways to change the magnetic field intensity in a closed loop. So by rotating the coil related to a magnet, by moving the coil into or out of magnetic field, by changing the area of a coil placed in the magnetic field, and by moving a magnet towards or away from the edge of coil. So for the second law, is Faraday's second law of electromagnetic induction states that the induced EMF in a coil equal to the rate of change of flux linkage, which E is the electromagnetic force, while meanwhile for the far is the magnetic flux and the n is the number of turns. The flux linkage is the product of the numbers of turns in the coil and the flux associated in the coil. So the formula for Faraday's law is given for the fine electric motor is same as like negative n and delta plus time. So the last and for the last topic, the last law. So last law states that the induced electromotive electromotive force with a different polarity induce a current whose magnetic field opposes the change in the magnetic flux through the loop in order to ensure that the original flux is maintained through the loop when the current flow in it. Named after in the Lenz's law depends on the principle of conservation of energy and Newton's third law. It is the most convenient method to determine the direction of the induced current. It states that the direction of an induced current is always such as to oppose the change in the circuit or the magnetic field that produces it. So, the Lenz's law experiment is to define the direction of the induced electromotive force and the current. We look to the Lenz's law. Lenz provides the experiment in accordance with his theory. So, for the first experiment, in he concludes that when the current in the coil flow in the circuit, magnetic field lines are produced. As the current flow through the coil increases, the magnetic flux will increase. The direction of the flow of the induced current would be such that it opposes the increase in magnetic flux. For the second experiment, he concluded that when the current carrying coil is in one and on the iron rod, and with its left hand behaving as an pole and is moved toward coil as an induced current will be produced. And for the third experiment, he concluded that when the pull toward the magnetic coil, the coil length decreases, which means that the area of the magnetic field decreases with the left motion of the coil is opposed when the induced apply the same direction. So to produce the current, the force is exerted by main side of the loop. To oppose the change, the current on the magnet must exert a force on the magnet. So the Lenz's law of application is when the Lenz's law application are of magnetizing. Some of them are listed below: eddy current balance, metal detectors, eddy current dynamometers, breakage system on train, AC generators, card reader, and microphone. So that's all from me. That's all from me for today, where we learn about some of the law and also the application and also when the explanation and so the history and the use of that law. So I hope for this presentation will help you all of you to study and encourage you to search more about this law more further. So that's all from me. So thank you and good night.